No, I know you don't count it. So story number one is it's going to be about AI acceleration. Okay? And the reason why it works for me as a topic is because I did my PhD on hardware verification. Okay, so I'm that old. Okay? So back in the time when it was cool to use an interactive VMware, no automation, okay? No SMT solvers. Yeah? Well before that, and you would type actual quantifier instantiation into a terminal, into an Emacs window, okay, not even a terminal window, yeah, into Emacs, to instantiate the quantifiers to prove some theorem, some RTL being equivalent to a suspect. Okay, so that's what I did. And I'm kind of getting back to that now. So I'm going to talk about AI accelerators. It's the hottest game in town right now. Okay, so the expectation is that this with whole business of training LLMs very specifically is going to get an investment in the order of $1 trillion over the next decade. So there is nothing crazier going on right now in computer science. Okay, and with the whole business of AI becoming quite enabling for other sciences, you could go as far as saying it's almost business in science. Okay, let me first give you a sort of brief rundown of the CV. So you just heard some from Laura. I'm going to give you the DOME version of the CV. Okay, so I couldn't find a DOME for the University of Saarbrücken or PhD. We really need to build one. So who knows what this is? Who can recognize it? A little puzzle, a little quiz. Who recognizes this picture? It's a famous university of computer science. Come on, people. No one? Not a single person? It's not Manchester, no. Not quite the star. No, this is ETH. You can tell from the lake and whatnot. So this is ETH, sure. So this is the ETH's dome. Okay. First one, come on. Like everyone knows this one, okay? Let's switch over for this one. It's still a bit of a difficult. It's not that easy for Americans, okay? But this one is very easy for Americans. CE, yes. So that's the used dome, okay? That's a ECE building. Yeah? So I worked there with Clark when I moved to ETH and then to Oxford, and I've been there until 2020. And, so something like 5 years ago, I moved to so. Okay, so I started as a consultant with them in 2016. That's been quite a while. So that's Amazon's dome. Okay, it's obviously the largest. My current role is with Annapurna Labs. So Annapurna Labs has a distinct name within Amazon because it's an acquisition. So it's a company that was called Annapurna Labs that Amazon bought at some point. And they do a bunch of things. They are not that well known outside of Amazon because they only provide their services within Amazon and you don't buy their hardware. So you use it when you create an account for AWS and you then sort of use AWS services and you're implicitly using the hardware. You're not ordering the hardware and putting it into your own data center. Okay? So I think the most well-known one is Graviton. So it's by far the most widely deployed server-grade ARM CPU. Okay, so you can think of this as being a UK success story in an American data center, okay, designed by Annapurna Labs. So these mostly get sold for price. Okay, so they are quite a bit cheaper for the same kind of workload than your Intel or AMD CPU. And they're really very large customers who just say, like, I want those savings, and they just port all this stuff over from x86 to ARM just because they want to get the efficiency of these Graviton CPUs. Okay? I mean, a good reason why they're so efficient is because they have big, large caches. That's sort of part of the story. Okay? So the other thing is better hidden is the Nitro system. So we are a good number of academics who work on the correctness of hypervisors. Okay? A good number of projects in that space. And quite frankly, AWS is very skeptical about the correctness of hypervisors to the point that we don't believe it anymore. Okay? So we don't believe that you can take, let's say, an x86 CPU or an ARM CPU for that matter, and construct an operating system that will securely isolate workloads from each other. Okay? So instead what we have done is we built hardware for that. that actually splits up a machine into time slices and isolates them from each other. We trust that hardware much more than we trust the piece of software that tries to do that. Okay? But the one I'm going to talk about today is differential and training. So that's a custom design chip for machine learning acceleration. I'm going to spend about half an hour on this, okay? And then I will switch over to how we would use formal methods to get some assurance about that part of the video. Okay? So I'm going to be really, really quick about this because most of it is a known story, like you've heard about 1,000 times. Okay? So people like machine learning, they do. And for reasons that are good or bad, I will leave it to form an opinion, like we'll comment on it. We like things to be large. And in particular, there was some hypothesis in the table that if you have loads of parameters in your model, it's good for you. Okay? So I think the final answer isn't done yet. There are a lot of people claim that, in fact, these parameters aren't really utilized and you could get the same performance in a model that's actually a lot smaller if you do it right. Okay? But in any case, there's customer demand to go from like what's sort of normal right now is that model sizes between 100 and 100 billion and a trillion parameters. Okay? And there is clearly demand to cross that 1 trillion barrier towards a 10 trillion mark. So I've seen papers that claim they have a model with 1 trillion parameters, but there's sort of data in there that this provides any utility whatsoever over the smaller models was very weak. Okay, but it will come. So pretty much a sure thing. And all of us know that sort of this is more than a 10x here, and the expectation is that the demand for this will pop up within 2 or 3 years. The 10x won't happen on the hardware side. Okay, so we won't suddenly have CPUs that are 10x faster. Yeah? So Moore's law is not what it works. Yeah? So our hypothesis is we need to make changes to the architecture and the software stack in order to deliver at 10x, not to sort of clock speed will go up to 30 gigahertz or something. Okay? So this is also pretty obvious and straightforward. So you're not going to use a CPU for that job. Okay? So a training run costs in the order for some of these very large scale models, costs in the order of $500 million in compute. And if you're spending $500 million, you're looking into savings. Everyone wants to save a dollar here or there if they're spending $500 million. And it makes sense to look at special purpose hardware in order to deliver that job, if you have that sort of spec. Okay? Obviously, you will all remember this started out with people just taking GPUs that they had for graphics and realizing they can speed up their machine learning workloads. But these cards have obviously long evolved into special purpose hardware for particularly training large language models. So the workload has various benefits. So if you look at what you're actually doing, there are many features of it that you can exploit in order to make this job more efficient. Okay? So basically what these things do is you load a large amount of data, literally the whole internet, okay? And all the videos you could find, anyone ever made, okay? Any audio recordings anyone ever made, all the data you can somehow grab, okay? You load that from memory, you do some computation on it, some matrix computation, and you store the result back, okay? So this isn't a sort of Turing complete type workload. Okay, so it's not general purpose compute. Okay, it's also embarrassingly powerful. The order of the data kind of doesn't matter. Yeah, so you're going to do the same thing on a larger amount of the data. So this means you can branch it out over tens of thousands of machines. For everyone, you know pretty exactly what you're going to do. There's no surprises. Okay, like all your inputs are fixed. Okay, so this is running a fixed program with fixed set of inputs. So you can predict this and optimize for like one run, okay? And you're not going to do it again. Yeah? So you just optimize for that particular run. So a lot of things you do where we optimize for unknowns, like we do general purpose compute, which are not necessary. You don't need things like order execution, because you know everything that will happen. Okay? Order execution has been designed in order to deal with unknown inputs or surprising inputs. Yeah? We can do a lot of software management for things that otherwise get done dynamically. For instance, validity of caches only makes sense if you don't know what's going to happen. Okay? But if you don't know exactly the addresses of everything you're going to load and store, why do you need a cache? Yeah? You can just manage it yourself, or you can have a compiler manage it. Okay? So, so this is a little bit confusing, apologies for this. So this whole business of AI experts in AWS started out with something called inferentia, which was purpose designed for vision models. Okay, this was long before LLMs that were historic. So people wanted to do things like face recognition and so on. In a way, it was more power efficient than you could do it with a GPU or with CPU. Okay, and then we figured out that there's obviously not just domain for demand for inference. So this means applying model to input data, but also to train model. And a new architecture was designed called training, okay, makes some sense. And the same hardware that we also use for training, so we call that training 1, okay? But the same chip is also used for inference. It actually works, so it was designed to deliver both jobs, okay? But we call the same chip for the inference workload inferentia 2, okay? Because we already had an inferentia 1. So inferentia 2 is the same as training 1, okay? And that's going to be inferentia 3, which is the same as training 2, so it's one off, okay? Just for confusion. So here again, the sort of story was it's going to be cheaper vendor alternative for a particular workload. So save $1 or $2, much like in the training case, in the gravity case. Yeah? So this game is now changing a bit, so we are announcing the training 2 / inferentia 3, remember these are the same. So these are announced to be released in 2024, and so we have mid-November now, and we're not going to do it between Christmas and New Year's, so we can sort of make an educated guess that this is going to happen. So this is something where you're going to get an early preview, okay? But it's going to land on the shelf soon. And so the key here with what we're changing in terms of the story is that training 2 isn't meant to be the more budget alternative, but it's meant to be performance leader compared to GPUs. Okay, so we're trying to make an effort here to rattle up the sort of established beliefs that you're going to use a GPU to train your LLM. Okay, and that's the fastest way of getting there. So this is sort of a big slide. Okay, so this is a sensitive bit of data here. So in particular, how does training 2 compare to your GPU, okay, that you might otherwise be on? Okay, as you can see, there's a good gap in terms of raw performance between the GPU and training 2. Okay, so this meaning, in addition to the sort of savings you would be getting, not just compared to the previous generation, but also compared to GPUs, you would also be in a position to have the best peak performance. So there's loads of adoption of this. So the sort of, I guess the most well-known is Anthropic and the cloud models get trained on training, but there's many more. So if you're a fan of brand name phones, there's many customers who are adopting this hardware for training. There's also sort of a good engagement with people who own these software stacks around this. The most well-known things are PyTorch, TensorFlow, and JAX. Okay, TensorFlow is sort of on the way out. It's not a cool game in town anymore. So you'd be using either PyTorch or JAX, and so AWS made an effort to engage very closely with the vendors of these stacks and work on the okay. So I'm going to talk a bit more about the hardware that's behind of this. So you want to build a new building, which is large, think sort of aircraft hangar size. You will look into buying nuclear power stations next to it, so you can deliver electricity for that job only. It's just for training LLMs. Okay? And then you're going to fill the building with racks like this. Okay? So these racks have custom networks, it's not just Ethernet. So we do point-to-point PCIe links between these racks. Okay? Then in each one of these racks, you have a bunch of servers. Each server will have a couple of these CPU casings in here, and then each one of these boards, you have a couple of chips, and then on each chip, you have a couple of cores. Okay? So it's interesting to sort of look at these chips. They are not like a normal CPU. In a sense, the closest thing you can think of in terms of CPU architecture is your Apple M architecture, meaning that you have the actual compute core, okay? And right next to these compute cores, you have HBM, that's high bandwidth memory. So it's DRAM designed for peak bandwidth, okay? So you optimize here for throughput as opposed to latency like you would on CPU, okay? So this is a sort of more abstract view of the same thing. So you have a host PCIe that connects to a modest regular computer that just runs Linux that you would be used to, but it's really just for management. You have these HBMs, they connect to a course using DMA, and you have this chip-to-chip interconnect, which is basically PCI bus directly connecting to the course. Okay? So as I said, there are no caches, instead of scratchpad memory, so explicitly managed memory by the programmer. I think like Transputer, maybe in Manchester. Okay. There's some relatively unsurprising vector and scalar engines basically just to help. The sort of big interesting thing is what's called the PE array. I'm going to say a little bit about this because it's so uncommon. Okay. So this is a paper that actually came from CMU. It's been quite a while. Okay. I guess sometimes the years take a while before they have the industrial impact. In essence, the idea is to line up a couple of computations on data before you store it back in memory. This way you save the transfer between the CPU and the memory. And that's a really expensive thing, as you will see in a second. Okay, so instead of like you load some data, you do some compute on it, you store it back, you would load some data, do loads of compute on it, like really like literally thousands of operations, and only then you store it back. Okay, and that gives you the seconds. Okay, so that thing is called a systolic array. If you're and we optimize it for specifically for geometry matrix multiplications, obviously. Okay, so by matrix multiplication, it won't surprise you. If you look at the sort of language models or vision models, it's most of the computations matrix multiplications. Yeah, and that's why we optimize this. All the rest is in a sense a little bit of decoration, right? So in large language models, you have a softmax layer that compares numbers and finds the biggest one, but it's a relatively small thing. Okay, so what's the key benefit here? The key thing, again, it's about saving data movement. Okay? Data movement is really something that's very slow and expensive. So this is a relative energy cost of additions, floating point additions, multiplications. Won't surprise you, multiplications more expensive than addition. But the sort of big elephant in the room is the DRAM. Okay? So note that this is a log scale here. Yeah? So if you can save a DRAM, basically you get a lot of compute for free. If you just save one DRAM. And that's a big, big deal when it comes to making computation more efficient. It's all about the memory access, not even so much about the computation itself. Okay? So remember, so we now build up a matrix of compute elements, and I'm going to just illustrate how this works with animation. Okay, because it's a lot quicker than trying to sort of explain how to set it up. And the example I'm going to first use is the vector matrix multiplication, which is not something you actually do in a large memory model, but it's sort of large language model, but it sort of gets it going. So in the hardware, so we have these lined up in a nice, neatly in a matrix. Okay, it looks very pretty on the sort of chip layout. 128 by 128 multipliers, basically. Okay? So we line these up like on a chessboard. Only instead of 8 by 8, it's 128 by 128. Okay? So, and then the trick is that you sort of fill in your operations in a sort of slanted way. Okay? So you're not going to hit the array basically in a horizontal fashion. Okay? But you slant it in order to make sure that the temporary results that you're getting out of here, like you're doing the first multiplication here, you get a first result, okay? And you will need that in order to do the next multiplication here. Okay, and that's why you feed it in this slanted fashion. Okay, and then at the end of this, your result pops out at the bottom of the multiplier. Okay? So you might wonder, like, hey, you know, it took me actually 128 clock cycles to go through that 128 array, that's actually pretty slow. They're not impressed, okay? Like this whole thing starts making sense if you feed it, if you keep this busy. Okay, so if you keep feeding, and I'm going to illustrate that with a matrix-to-matrix multiplication. Now we're actually going to use all of this simultaneously. So again, it's slanted. Okay, so I'm trying to illustrate this here with these colors. So you're going to feed this into your multiplier array. Okay. As you can see, sort of as the data flows through the multiplier array, you're actually keeping all the multipliers busy all the time. Okay, and that's a trick to it. You need to arrange all your computation such that these waves that hit the multiplier array keep coming and never stop. Okay, and then basically you're going to do 128 by 128 arithmetic operations simultaneously per clock cycle. Okay, and your best CPU with an out-of-order scheduler, yeah, when it really hums, is going to do 2 of these per clock cycle. Okay, so we're going to rub it in. Okay, just going to say it again because it's slightly incredible. Okay, so we have these. So just take as an example. Let's say 512 by 128 to 128 by 128 mod. Okay, so we have 16,000 arithmetic units. So our potential speed up is 16,300 times over this sort of naive sequential version of that. Okay. So this runs at speed. Okay, it does 16,000 operations at speed and at 3 gigahertz properly. Okay, there's no delay because you're not waiting for a cache to load a cache or anything. Okay. So to make that happen, there's quite a bit of a software stack that we need. So at the bottom you have that hardware as a runtime on top. So you don't just do this on one core. This was just one core. Okay. Remember, each chip has multiple cores, and each server has multiple chips. And then you have multiple servers in the rack, and you have many, many racks in the data center. And customers rent in the order of 10,000 of these in order to do a job. Okay, so this means you need to distribute your workload over 10,000 machines with thousands of these cores. And in order to make that happen, we have a runtime orchestrator board. Okay? And on top of that runtime, you have things like PyTorch or JAX and so on. So next to that, you have a compiler. So compiler researchers tool again. Okay? That takes in a Python program, that's what we compile, and turns it into machine code for this architecture. Remember, we know everything ahead of time, because we know the data, and we know the code. So this compiler is a lot more work than your normal GCC or plan. Okay? It fully makes all the decisions for the CPU. We can tell exactly ahead of what the CPU is going to do. Okay? So I'm now going to do a bit of a switch. Yeah? Happy to take any questions about the hardware. We're very open about this. We give you very detailed architecture specs. If you're curious as to sort of how exactly the hardware looks like. So I'm going to switch over and I'm not going to tell how we use formal methods in order to deliver these features. Okay? So this is work relating to Nitro and the sort of use of hardware in order to isolate workloads from each other in a shared tenancy setup in a data center. It has been a while, so this is 2018. There's a journal version of it right now. So this is about the boot code that gets actually manufactured in hardware. So these bugs in there can be quite costly because you have to worry about the actual physical hardware for data centers to find hardware. So the work that we're going to present today is not that. Instead, we're going to talk about a paper titled Neural Model Checking, which will be presented at NeurIPS in December. So you're going to be the first people to see it. Okay? A month ahead of time. Okay? So I'm going to talk very quickly about model checking for RTL versus the long story here. But the industrial history there is, I guess, the most extensive one in formal methods. Yeah? So the industry has invested a lot of money into doing formal verification for hardware. It's typically something you do per module, so this means identify a module, try to think what should it do, you spec it out, try to verify a module, okay, in some way in isolation. Very risk specific because Verilog isn't really very modular. It's a sort of semantics discussion we can have saved for another day. But there are also some interesting properties to be checked that are cross-chip. Okay, so you remember I told you that these scores are in rack and many racks, and they're linked through these PCIe links. So for instance, one of the properties we looked at is if a protocol that makes these decisions where to send your packet is deadlock free. Okay, that's a property that only makes sense in a cross-chip fashion. Okay, generally, liveness properties are a lot more interesting than safety properties. Okay, I'm not obviously saying that safety properties don't matter, but liveness properties are the one that are really the most annoying. Okay, if you have a bug there. So you need to imagine you kicked off a training run on a large cluster of these machines. You expect the bill for this to be $200 million. And after a week, it stops. It just gets stuck. Okay, you look at the utilization of the cluster, and it's just dropped to 0 over there. And you don't know why. Yeah, you don't have the visibility. You can't look at the values of the registers, on a manufactured chip. Then you're going to probe them. Yeah. So these sort of bugs are really, really hard to look at. Yeah. If the thing then lost, it's not going to long-running computation. Okay. So getting liveness bugs out of these sort of designs is something really important to do, and very, very good return for investment for using formal methods. Okay. Unfortunately, on the other hand, if you look into buying tools for doing formal verification of these sort of designs, for reasons that are quite clear to me, they tend to be quite alright on safety properties, but most of them are actually quite bad, surprisingly bad, when it comes to liveness properties. Yeah? I can sort of see that there's some economics here, as in, like, if you start out doing formal verification in a new business, you're sort of trying to make buying decisions. You will obviously not immediately write the most sophisticated properties. You're going to start with something easy, okay? And the easy thing is going to be the safety property. This is what you will write, okay? And then you'll try out a bunch of tools, okay? And you will go make a buying decision for what works well for those safety properties that you've just written, okay? You will probably not benchmark it on liveness properties because you couldn't figure it out so far. Okay, that could be, so I'm just speculating a little bit here, that could be the reason why the support for liveness properties in these tools that you buy isn't that great. Okay, that's something that unfortunately we did run into and we didn't have a good time. Okay, so let me just give you a very trivial example to fill this into a bit more life, make this a slightly bit more concrete. So this is a simple delay module. So basically, you reset it, and then at a certain point in the future, which is configured at compile time, it will produce a signal, okay, which comes here as an output of this module. Okay? So hardware doesn't have initial states. Okay? Hardware is just basically powered on. It's in some sort of non-deterministic state. In order to get it into any state you want, you have to reset it. So one pattern you will probably find is that all of these modules try to run a reset signal. Okay? In addition to having a clock. Okay? So the property of interest of this most trivial example here is that so GF is LTL, so globally eventually you get a signal, so the signal will keep coming forever. Okay? But you can only actually guarantee that if you stop resetting it. It's a bit trivial. Okay? But if you think about it, obviously if you keep hitting reset, then the signal will not necessarily come. Okay? So this is an assumption you make about the environment. So basically, this is a precondition. If you were to think of it as a contract with its environment, and this is a guarantee that the module will reverse if that precondition works. Okay. So this would be. So this is the simplest example I would come up with for relevant liveness property. Okay. So how suppose you take more complicated versions of this, or modules, bigger things like routing protocol, or whatever, something like this. How would you go about verifying this for a given implementation? So here's a sort of set of options. It's frankly not a long list. Right? You kind of had hoped there would be more bullets on the list. Well, it's not that long. Okay? Good old BDDs, ready bind. That's still an option, it's still on the table. You can do bounded logic with SAP and SAT. You can take your favorite automated reasoning engine solver and hit it with an unrolling of your circuit. The obvious issue with this is that while SAT and SAT solvers really did make a lot of progress, you will have a bound here, okay, which means that you don't actually get proof, okay? But you want to get, hey, I didn't find a bug up to bound that I made up, okay? So how are these things doing on the example before? So IC3 is not really made for liveness properties. So yes, there is a paper that says I do like IC3 for liveness, but it's I would say it's not an open problem. Really only works for safety right now. So with PNC on this example, the thing I had on my previous slide, so with a parameter at 750 here for n, so obviously you kind of bound with 1 is at least 750, right? When you see the signal happening once, you can see it the second time. Okay? And 750 isn't a realistic value. Like this thing runs at gigahertz speeds, you're probably a couple of hundreds of thousands, okay, for these sort of parameters in a realistic setting. And for 750, it doesn't finish with any SMP or SAT solver. Try to run. Okay? And this is really, really very simple. Okay? Like you can't make it any dumber. I couldn't think of a simpler example. Alright? Okay? Good news is BDDs does this in seconds. Okay? But everyone also knows that BDDs will only work on trivial stuff. But if I blow this up to a larger, more realistic circuit, like I put in some arithmetic and work on it. But obviously the BDDs won't do it. Yeah? But sort of the rule of thumb still applies that if a thing fits into a BDD, then it's easily quick. You can sort of expect BDDs to be linear in the sequential depth of the circuit. So this thing will need 700 something iterations to reach a fixed point, but it's alright. Okay, so that works. Yeah? But if you make it 100,000, 200,000, it's not going to work anymore. It's just going to work. Okay? So the industry did come up with an answer to this. Okay? So this is not a new problem. The answer is you write proofs. Okay? And in fact, all the work in formal method in Amazon is all about proof. Okay? Like the whole business, you're going to find some bugs, doesn't matter in Amazon. So Amazon will hire literally hundreds of automated reasoning researchers, people with PhDs, over the next few years. Okay? We are very, very keen to hire all of your graduates, if you have any that are looking for jobs, please see me straight away. Okay? We are really, really hiring a lot. And all of them will be hired for proof. Proof and proof only. Okay? It's not about bug finding. Don't care. Okay? If you want to find a bug, go get yourself a fuzzer. Okay? We want proof. Okay? The answer here is you're going to write a proof, and for safety, the obvious thing to do is you're going to write inductive invariance. Okay? So, and then the nice thing is that you can use a BMC instead of using a bound 750. You just have one transition, so two copies of the transition relation. So one copy of the transition relation, basically, 2 time frames. Okay? So here's a trivial example, just to humor you a little bit what I mean. Okay, so if you have this is a little snippet outside of a ring buffer, which is a staple in hardware design. So if you're renaming then something that's out of the buffer, so the count, so the number of elements in the buffer goes down. If you're writing, it goes up. And note that both of these might be on simultaneously in the same context. So you might be reading and writing, and that means your count actually stays the same. Okay, so the minus and the plus cancel each other out. Okay? The thing is full if the count is 16, or whatever number of elements you have in that buffer, and it's empty if the count is 0. You're going to need some environment assumptions. For instance, you're not going to read when the thing is empty, don't do that. Okay? And you're not going to write when the thing is full, don't do that. Okay? So that's just an SVA syntax for the implication. Okay? And then you can prove a few properties. So, for instance, you might want to know, this seems very easy and simple, but the count never reaches 17. Okay? The bad news is it's not inductive. Okay, so you have to strengthen it to be something that becomes inductive. For instance, if you then strengthen this to the count being between 0 and 16 inclusive, then it becomes inductive and you can prove it with just one transition. Okay, because that's all the C3 with any other favorite density probability, right? You'll be able to prove this very easily within fractions of seconds. Okay? But you have to write these invariants. Okay? So now what do we do for liveness? If we've got something for safety that's at least actionable, meaning you can hire people who will write these invariants for you. So it's not quite standard yet for doing that for liveness. Okay? So people don't really know how to write proofs for liveness. But my hypothesis is we shall have ranking functions. Okay? Ranking functions, as in the ones used by Turing to argue determination of Turing machines, that kind of thing. Okay? So we want well-founded relations over states of the hardware, and so thereafter. Okay? So these basically map a state, let's say the value of a counter, which is seen to, let's say, a natural number. That's easy when you finite state systems. You make it unsigned, but it's trivially bounded from below. 0 is the smallest number you get. And then you want to basically just check out this rank that you have for each state decreases strictly with the bounded ball checker. And you're back in the game where you see one transition, like you did for the safety invariant check. Okay? So basically you get the liveness for the same cost as you did for the safety property, but you need to come up with these ranking functions. Okay, so here's a little example. So this is the delay module again, and this is the same property that I've shown you before, and it has a proof of that property using a ranking function. The ranking function is quite simple. It's n minus c and t. There are two cases here. One is obvious, namely that you're just counting upwards from zeros. You did a reset, you start at 0, 1, 2, 3, 4, 5, and so on. At some point you reach n, and then the thing produces a signal and you're done. Great. And it's very easy to see that your rank decreases as the counter goes up. Okay? The more subtle case, which isn't obvious, is the fact that the counter might be bigger than n if you didn't reset. Okay? Then how do you know that the thing will actually still have this liveness property? And the answer is this also works because the counter wraps around when it reaches the end of this register. Okay? And so this thing will be negative, and then if you pass it over into an unsigned integer, you will actually see that this number decreases as the counter increases. Okay, so that works as well. So these two cases are obvious. So you look at this ranking function. Okay, so it's a very simple ranking function that covers two behaviors. One of them is obvious, the other one is obvious. Okay? So great for this trivial example, but what about more complicated properties? Sorry that the automaton here is a bit fuzzy. It wasn't when I looked at it on the screen. The obvious thing, if you wanted to have more complicated properties, let's say LPL, or the industrial version for this SVA, SystemVerilog assertions, you go hire a nuclear automaton, okay, pretty straightforward. So if you take this property, it produces a free state automaton, and there's like a gazillion tools out there that will translate your LPL, or let's say, property into automaton. They're pretty decent by now. Okay, so the tool they're using is called Spot. Okay, again, apologies for the figure being a bit fuzzy. I'll put it on the screen. So the process you're looking at works as follows. So basically, you take the model of your circuit, you combine it with the nuclear automaton for the negation of the property. So that's not phi here. So they get linked together. Okay, so this means they form a product machine. Change state in lockstep. Okay? So far so standard. So the non-standard part is here. So we're going to hook up all the outputs and observables from the model and the automaton with a neural network. Okay? So now we're going to use a neural network to prove properties of hardware that's used to train neural networks. I hope that's clear. Okay? So feeding all of these observables to a neural network. Okay? And my expectation is that the neural network will produce a rank. Okay? A rank that's bounded from below, get it for free because it's an unsigned number, and that decreases strictly with every transition. Okay? So if I have that, I can take the neural network and use Z-free or another SMT software to check whether it meets these conditions of being a ranking function, and have formal proof that my property holds for all executions. And just to be clear, this is not a heuristic of some sorts, but again, actual proof that the property so this is a learn and check loop. So basically you start with a model and the automaton in parallel. You randomly sample it, okay, just using a simulator. You give that to PyTorch. You learn a model. Okay, the initial model might be wrong. Okay, therefore you give it to Z3. Okay, we use bitbuzla, and you check if it's indeed a ranking function for your given circuit. Okay, if it is, if your SMT solver comes back and says unsat, then you have formal proof that your circuit satisfies your temporal property. Okay, if not, you get a convex sample satisfying your assignment. You add this to the data set and you retrain. Okay, you've done data set documentation for your SMT solver. So the neural architectures we use are pretty straightforward. So basically just use a bunch of layers of values and so on. A standard feed-forward network. You don't need to spend all that much time on obsessing over what neural architecture to choose because there's AutoML. So basically AutoML searches for a space of neural architectures for you. Okay, obviously that space is infinite, but you only care about the sort of smaller ones anyway, right? And it will find a reasonably small, maybe not the smallest, but a reasonably small neural architecture that just does a job for you. Okay? This is actually interesting to get a small one because the benefit here is that if it's small enough, you can even read it. You can even read off a ranking function. Yeah, that's sort of human intelligence. Okay? So again, sorry for the fuzziness of this. It looked okay on my laptop. So just in summary, what we're doing is we're gathering training data using random exploration. So this is basically a reinforcement learning setup or a CGAT setup if you want to look at it with the eyes of some of the formal methods. Okay? For example, guided abstraction function. You don't need to have a pre-connected data set. You can start from nil. Okay? Just you don't need to have you don't need to be an owner of data or something like this. Okay? You compute a loss and you set up a loss function. So the benefit of a ReLO here is that the ReLO is always bounded by 0. So again, you get the fact that the ranking function is bounded for below for free of charge. And in essence, what you were just looking at is a transition. So the prime here means next state, as is common in moderated reasoning. So basically, you're looking at the ranking of your next state minus the ranking of the previous state, and that needs to exceed some epsilon, okay, which is a constant you choose, which kind of doesn't matter as long as it's 0. Okay? When you give this to your training system and say, hey, go optimize this, find something that gets as close as the loss needs to be as small as possible, and it's bounded by 0, so this means 0 means there's no loss. Okay? And then we have a candidate that we can give to our form EMC with bounded one. If you get a common example, add this to your data set and try again. But in fact, in practice, we found that in most cases, this even works in the first iteration. If you did some good random exploration, you basically get with one shot, you get a ranking or complex array. So here's some experimental results. So this is on 200 verification tasks. Okay, so that's your standard cactus plots. If you haven't seen these before, so this is a sort of this is a time budget. Okay, so you give it a time budget, a timeout for each job. Okay, not in total, but for each job. And this is the percentage of the jobs of these 194. So if you get here, when you finish them all, and if you're here, then you haven't finished even 10%. Okay? So generally, data points that are lower to the right are better. Okay, so you want to be a good tool is in this corner, a bad tool is in the middle. Okay? So it's all liveness properties. Okay. So as I said, we use random exploration. It's done using a tool called Varilator, which is a pretty standard simulator PyTorch for training. bitbuzla is a solver, but C3 is actually not much worse. And eBeamC to make the SMT formula from the Verilog. Okay. All of these are freely available, so none of this is proprietary anyway. So we do comparison with ABC, which is a tool from Berkeley. Okay. And USMD, and this is frankly freaked me out a little bit. So that when we started this, but you know, good old USMD, which I mean, Alessandro is going to be here, I believe, on Friday. You can tell him the good news. So good old USMD was in fact still very competitive for single jobs. And it's a little bit sad that the academic community hasn't done much better than USMV since then. And we also included 2 commercial tools where Amazon has acquired licenses for these tools in order to do this sort of job in this comparison. Okay? So obviously, the bottom line is obviously that the method that I just presented always wins. That's how it goes. With these talks, okay? Never the other way around. But you can see, maybe just deep diving a little bit into the data, you can see that for initially on sort of easier jobs, it doesn't do that well. Okay? And that's because like this whole thing of like doing a random sampling, setting up PyTorch, getting this going, doing the training, all of this has a bit of a constant overhead, and on very, very simple properties that just doesn't pay off. You're just better refitting them with a BDD and you're all set. Okay? But it does pay off the second it gets harder. Yeah? Then the tool performs a lot better. Yeah? The thing which is that did shock me quite a bit is that USMV is still very competitive, in fact. Okay, so that's in CL. We were a little bit disappointed by ABC's performance because it did win hard verification competitions, and we sort of expected it to beat USMV. But on like we really couldn't find any benchmarks where this would really shine through. It could be that it's benchmark bias. I don't want to rule that out, but we made an effort to make the benchmarks broad. Okay. So one of the commercial tools, and it was also a bit disappointing, and I'm not going to name it, unfortunately didn't finish a single benchmark, not one. Okay, to the point that we were really very worried that we were just not running it. Okay? So we try to add more simpler benchmarks or to see it at least finish once. Okay? And unfortunately we found that sort of even very, very simple properties from our regression test suite, which is running fractions of seconds, which are really just there to test the tool, would often not work. So the tool is very good at, I mean, it's reasonable as it performs like you would BMC to perform on properties that get refuted, that you get a countersample. But on anything that requires proofs, even if it's comparatively simple, it just would not want to train. And that made us quite a bit sad. So this tool seems to be really just designed for bug finding. Okay? And it's still very expensive. So the other tool, which is even more expensive, so that's this gray line, did actually quite well. So we were not unimpressed. It has some weird auditing, and that's in the form of this nearly straight line here that you can see here. So initially it sort of performs very similar to ABC, as if you were thinking it's probably using very similar algorithms, so it's all black box, you don't really know what's inside. Okay? But then at some point, it just gave an answer. It said proof after a magic number of minutes. Okay? And so we try to find out what's going on here. And so what happens here is that the tool very heavily makes use of portfolios. So this means it has many different algorithms implemented, and it heuristically switches between them after it has tried this certain algorithm for a while, and then it switches over to another one. And the one it switches to after something like 15 minutes is just very good at these sort of properties, and it can actually solve a lot of them. Okay? So that convention is very impressive and doing extremely well on conventions. Not all of them though. So the second you sort of fall out of this particular heuristic gets triggered by, then the performance isn't as impressive anymore. Sort of the hardest benchmarks, it's not doing that. So, okay? But yeah, so this commercial tool did extremely well. And we sort of felt that if you had control over the portfolio, you could just pick out that one algorithm that just does so extremely well, it would probably deliver a line that's here at the bottom, and then spikes up here. Okay, that's probably not a good track. Yeah? So not an unimpressive result from that commercial tool. Okay? I'm going to end on this slide here. So this is also brand new, also yesterday, okay, to November 12th. So we will hand out $110 million in grants to universities, okay, to researchers such as yourself. So I'm very sorry you're not going to get any money from this representative. This is, as I said, brand new hardware. So we are now reaching for performance leadership. Okay, so it's not just about saving a bit of money when doing the training, but we hope to get across that the hardware that we've built is actually in a position to deliver the best of class performance. Okay? This is non-trivial. Okay? So you've seen me animate through that systolic array, 128 by 128 multipliers. Okay? Programming this is really very non-trivial. There's very non-trivial work that needs to be done here, research that needs to be done here in compilers and setting up these models so that you can actually get that multiplier array to keep the seed. Okay? So you can't just take your GPU model, push a button, and it will run. Okay? It's not how it is. Okay, so we need the help from universities in order to show off the power of the hardware. And to that end, we will provide a non-trivial amount of money to university researchers globally to support research using these training chips. Okay? So if you work in program analyses, if you work in compiler construction, decision procedures, then this is for you. Okay? So we're hoping that you will submit an application, so the money will. So traditionally we give these explanations, so there's no heavy admin or anything like this involved. Okay? You don't need to hire auditors or whatever nonsense you might have to do with sort of more heavier grant schemes. And we want you to look into how to make that piece of hardware shine. Okay? Thank you very much.